Start பண்ணலாமா sir? Can I start?
Yeah, yeah, we can start it.
Okay. A very warm afternoon, dear participants, colleagues, and fellow faculties. Indeed, it's a great pleasure for us to rejoin in this webinar today. And I'm happy to introduce our speaker for the session. Our speaker has completed his PhD from Vanderbilt University, and he was a research associate there. And in Fisk University, he was working as a research scientist in Department of Physics and Life Sciences. And it's actually a crown in his thing that he has solely managed and classified as $100,000 national-sized foundation-funded material engineering project. And right now, he is working as a research fellow in National University of Singapore. To have a glimpse about his achievements, he is a material scientist and research fellow with over 8 years of experience managing large-scale and multifaceted material synthesis and engineering. He has credits of authoring articles and is a lecturer in publication of peer-reviewed journals. He leads and monitors teams. He has established business and academic partnerships and deploys processes, technique improvements, and solutions for overall performance. Dear participants, I take privilege in introducing Dr. Saumitra Vajandar, Research Fellow, Center for Ion Beam Applications, National University of Singapore. Sir, I may now request you to take on the dais. Thank you.
Yeah, thank you, Professor Ramya. Thank you for the introduction. And before I begin, I would also like to thank the other organizers of this webinar, especially Dr. Professor Philip Raja, for giving me this chance to talk about my work in NUS today. So like Professor Ramya said, so my name is Saumitra. I was in the US. I did my PhD in the US. I worked there for a while. I have been in NUS as a research fellow since 2015. So it's been about 5 years now. And I work in the Center for Ion Beam Applications, that is CIBA in short for you. That's a center in the Department of Physics in the National University of Singapore. And the talk that I want to share with you today is going to be on ion beams. Why ion beams is because our center mainly works with ion beams and its applications. But what I want to do today is I want to give you a materials perspective of ion beams. Am I audible, Professor Ramya? Okay. So so I want to share with you a materials perspective of ion beams and the kind of research and work we do in CIBA. Okay, so the outline for my talk today is going to be, I'm going to give you a brief idea or overview of the facility itself, the different beam lines that we have, the different kind of systems that we, systems and techniques that we typically run in CIBA. I will then move on to why we use ions over electrons and what are the advantages of using ions or electrons. From there, I will move on to some of the commonly used materials analysis techniques that we employ in CIBA. And some of them are techniques that I typically work on, followed by some of the imaging and mapping techniques that we usually work with in CIBA. From there, I will move on to a technique called as proton beam writing. This is a technique that was started and developed in CIBA by one of the professors, senior professors, and this was started back in early 1990s. And it's mainly a materials modification technique. So I will briefly explain or give an idea on what proton beam writing is. And then I will move on to a specific technique, materials analysis technique called as Rutherford backscattering or RBS. This is a technique that I mainly work with. Most of my projects in CIBA have been on RBS. And within RBS, I want to explain a bit on ion channeling. This is a subset of RBS technique, and I want to kind of touch upon what ion channeling means. and how it can be used to identify and quantify lattice strain. Okay. Following this, I will then move on to one of the first projects I worked on in SIBA, which was on germanium-lead thin films. And this project actually uses a lot of RBS and ion channeling technique. So, which is why I am touching upon these techniques here first before I move on to this project. And lastly, but not least, one final slide on a new kind of a therapy that it is a hot research topic now. It's called as proton beam therapy. And we at SIBA are kind of working on developing this therapy further. So I'll just give a brief idea on what proton beam therapy is. Just one slide to end off my presentation. Okay, so that's going to be the outline for you. Looking at the facility itself. So this is what the SIBA facility looks like. Okay, so this is a schematic. So this is 3.5 MV singletron accelerator that we have, or in other words, it's a single-ended accelerator. This was purchased from a Dutch company called HVEE. We mainly work with, so when I say accelerator, what we do is we generate particles inside the accelerator and we accelerate it at high energies, typically on the order of 2 to 2.5 MeV. We work with mainly two kinds of particles, protons, which is H plus, hydrogen plus, and alpha particles, which is helium plus. We do have oxygen and nitrogen in there. So sometimes we do use oxygen ions and nitrogen ions, but our main work focuses on protons and alpha particles. We generate these particles in here, we accelerate them. This is a 90-degree magnet or an analyzing magnet. What this does is this will then filter out the charge that we want. So let's say if we want H plus, we can filter it out using this magnet, or if we want H2 plus, we can filter it out using this magnet. So that's why it's called as a filtering magnet or an analyzing magnet. And we then get the beam through this magnet and up to here. This is a switching magnet. From here, then we have 6 different beam lines that we can get the ion beam into. And as you can see, each of these beam lines have different kinds of end stations, and we can run different kinds of techniques and different methods in each of these beam lines. So starting from the first one here, this is an ion beam analysis beam line where we do RBS, ERDA, elastic recoil detection analysis for hydrogen detection and ion channeling measurements. Then we have this beam line here, which is a new beam line. This was commissioned just about 2 years, a year and a half back. This is the microradiobiology beam line or the proton therapy beam line. And this is where we put in live cells and we expose them to high energy protons. And then we see how these protons change the cells. What is the effect of these protons on these cells? So that's a proton beam therapy beam line. It is still kind of under development, but it's functional as well. Then we have the proton beam writing facility. So this is the materials modification line that I talked about. This is where we have we use these proton beams. We use protons at high energies to create microstructures or nanostructures in photosensitive materials. Then we have the cell and tissue imaging beam line. Now this beam line is not very different from this one. The only difference being that here we cannot put in live cells. So this setup here is an open air setup. So where we put the cells in open air, not in vacuum. Whereas here the cells go in vacuum, so they are pretty much dead. So we have cells, cell tissues, or cell membranes that go in here. And what we do is we then have proton beams or alpha particle beams to, we use these beams to image these cells, map these cells for certain elements that we want to map out, or certain contaminants that we want to map out. This one here is a nuclear microscope. This beam line is mainly used for for PIXI, which is short for particle-induced X-ray emission. In SIBA, we call it as proton-induced X-ray emission. because we mainly use protons for Pixie. But we can also do RBS and ERDA and ion channeling measurements here. And I mainly work on this beamline here. This is pretty much most of the time, most of my time is spent on this beamline. And then we have this last beamline here, which is the high resolution RBS facility. This one is kind of a special system where we can make, for example, if you have a thin film on the order of 10 nanometers or 5 nanometers or even lower, and you want to measure its thickness and measure its composition, this system works best for these kind of samples. And so this has a very good energy resolution and a very good depth resolution. One other thing that is kind of different here is that these 4 beamlines, the second, third, fourth, and the fifth one, they are all focusing beamlines. So if you see here, and this will be more evident in the photos I show later on, there are these quadrupole magnets on each of these beamlines. So what this means is that we can have a broad beam setup where the ion beam is just a broad beam spot, or we can focus this beam using these quadrupole lenses down to a beam spot which is on the order of 1 micron or even lower, submicron beam spots, and then use this focused beam to scan the sample and then collect or either map an image out of it or collect data out of it. Whereas these 2 beam lines, they are not focusing beam lines, they're just broad beam setups. So we just use broad beam, get it in the chamber, run the technique, run the method, collect the data, and that's it, we are done. So we have 4 focusing beam lines and then 2 broad beam setups. And then each of these beam lines are actually also measured by the angles. So, if this is a 0 degree here, so this one is -10, this is a 10 degree, this is 20 degrees. So that's how we call these beam lines. This is the 30 degrees, this is 45, and then this is 90 degrees. So that's how we label them in our lab. And then, as you see, with these 6 beam lines, at any given point in time in SIBA, we will have research areas or research work focusing on a wide array of domains. So we could be working on micro nanofluidics, or it could be photonics, or micro machining, or biophysics, or materials characterization. So at any given point in time, the kind of applications that we have at SIBA, they span a wide variety of interdisciplinary areas that go all the way from medical research to microengineering to different kinds of materials analysis techniques. Okay, so that's kind of a schematic of the SIBA facility for you, and this is the lab in reality. And of course, photos kind of don't do justice to the lab. It's a lot more better when you see the lab in person. So what we have here is, this is the entire array of beam lines. Right at the back here is the singletron accelerator, the single-ended accelerator. This is the analyzing magnet that I talked about, the 90-degree magnet. This is the first beam line, the non-focusing beam line. This is the proton beam therapy beam line. This is the one that was commissioned just about 2 years back. So this is the one where we are working on the proton beam therapy concept. This is the proton beam writing beam line, the materials modification beam line. And then here, it's not very clear, but you have the 30 degrees, the nuclear microscope here, and this here is the high resolution RBS setup. So it is more clearly seen here. So this is the high resolution RBS setup that we have. If you look at the proton beam writing beam line, like I mentioned, that's a focusing beam line. So we have these four quadrupole lenses set up on the beam line, which are used for focusing the ion beam. We see the same setup on the nuclear microscopy beamline as well. So this is the one that I mainly work on. But here we have only 3 sets of quadrupole lenses. And so this one also is a focusing beamline, but this is more of a general or generic or a universal beamline in SIBA. So what that means is we don't only use this for focused beam experiments. I use it for RBS, I use it for ion channeling measurements, I use it for ERDA, depending on what kind of detection system we have in there. So this is more like a generic beamline, whereas compared to this is more like a dedicated beamline. So the kind of focusing ability you have in this is much better than the kind of focusing ability you have here. So here they have even achieved a focus beam spot of as small as I believe it was 19 nanometers by 40 or 45 nanometers. So this is purely dedicated to proton beam writing. So although we can do RBS measurements here, but we are not allowed to do that. We only use this for proton beam writing. Whereas here we can do all sorts of experiments. So this is the chamber, a blow up of the chamber of this beamline, and so here you can see that there is an RBS detector already placed inside. This is the Pixie detector here. The beam comes in this from this direction. Okay, it comes from below the detector. You place the sample in the center. It interacts with the sample, and then you collect your data from the RBS data from this detector, and then the Pixie data from this detector. And then if you want, you can always put one or two more detectors in there, and then collect more data from other techniques. In fact, a couple of years back, we also managed to we put in a gamma detector on there. So we were running gamma, that is proton-induced gamma emission, RBS and Pixie at the same time. We had a human tooth sample that we were analyzing. We were analyzing fluorine in the human tooth sample. So we were doing gamma experiments. So point being that this beamline, this beamline with this chamber, it's a universal beamline, and we run different kinds of techniques on this beamline. So the focusing ability also is not exceptional. Like we get about a micron. I think if we push it, we can go maybe sub-micron beam spot sizes. But typically we work with 1 to 2 micron beam spots on this beamline. So that's the beamline setups in SIBA. And like I said, it's this lab is worth seeing in person. Photos don't do justice to the lab. Moving on. So coming on to the idea of why we want to use ions over e-beam or electron beam. So this is a simulation of a beam travel path inside a biological cell. Okay, this was done using a program called DEEP, or Deposition of Energy by Electrons and Protons. And here, instantly, when you see these two images, right, this is for 50 keV electrons, lower energy electrons, and this is for higher energy protons. So electrons being much lighter than protons at a lower energy, the moment they enter the cell, they start to scatter around, right? And by the time you go down to order of more than 100 nanometers, compare this to protons. Okay, so now you have 2 MeV protons. Protons are much heavier than electrons. At higher energies, what you get is a streamlined entry into your cell, right? In fact, if you look at like 200 nanometers or 400 nanometers, the scattering is practically insignificant. When you go down to 1 micron depth, you will have some amount of scattering. It's about 10 nanometers or less, but much better than what we see in electrons, right? So you have this streamlined entry effect into your material with protons. Added to this streamline effect, if we also take a look, if you go one step further and we take a look at how the energy loss happens in for MeV protons, for 2 MeV protons into a material, this is what we get. So this is a SRIM simulation of about 10,000 protons at 2 MeV into PMMA. So as I said before, as they enter, the scattering is hardly significant, but as they start to slow down at the very end, they will deposit all of their energy and they will come to a complete stop. And that gives rise to this peak that we call as a Bragg peak, right? So you have these two distinct effects that come with high energy protons entering into a material. You have the streamlined entry effect with minimum scatter or minimum scattering, and then you have this huge peak at the very end where they come to a complete stop and where they deposit all of their energy. So these two effects basically add up to give a huge advantage of using protons for proton beam therapy. And this is something I will explain in my last slide. So this is exactly the two distinct advantages of why protons become, or high energy protons become very useful when it comes to proton beam therapy. And we cannot use electrons for this. Electrons will not give you this effect, right? So that's why that's kind of a distinct advantage of using protons over electrons. Um, So moving on to some of the techniques that we typically use in SIBA. Okay, so and these are the techniques that I work with most of the time, and also these are the most commonly used techniques in SIBA. So we have PIXI. Like I said, PIXI stands for particle-induced X-ray emission, but in SIBA we call it as proton-induced X-ray emission. We have RBS, or Rutherford backscattering, and then we have STIM. STIM stands for scanning transmission ion microscopy. And if you look at these two graphics here at the bottom, they kind of show how PIXI and RBS works. Okay, so for PIXI, we have an incoming proton. It goes straight in. So this is at 2 MeV. So it goes straight in, knocks off an inner shell electron. The outer shell electron will then fill up the gap and give out a characteristic X-ray, right? RBS, you can have RBS with protons or alpha particles. In our case, we typically use alpha particles. So you have a 2 MeV alpha particle coming in. It will go right up to the atomic nucleus and then backscatter from the atomic nucleus. By detecting the energy of the backscattered alpha particle, we can then identify which element was present in your sample, right? So if you have gold, gold will backscatter this alpha particle at a much higher energy compared to silicon, right? So if we know the backscattered energy, if we have calibrated the backscattered energy, we can exactly identify which element we have in your sample. So that's just roughly, to give you a principle of what RBS is about. And then on any given experimental day, this is the typical setup that we will have in our chamber, right? So we have an incoming ion beam. So at this point, it's just a broad beam. We have a sample in the center. This is a fairly thin cellular sample. The beam is focused down to a small beam spot, typically on the order of 1 micron. We then scan the beam along the surface of the sample. When we do that, we are going to have three things happen at the same time. We are going to have a backscattered signal. So some of the ions will get backscattered. The RBS detector will detect these signals. So we have an RBS signal coming out, giving rise to this RBS spectrum. Then we have the PIXI detector, which detects the X-rays coming out from the sample. So this gives you the PIXI signal, the X-ray signal. And then we have one more detector placed behind the sample, off the axis of, not along the axis of the incident beam, but off the axis of the incident beam. So we call it as an off-axis STIM detector. And this will give us a STIM signal, which looks something like this. So this detector is not any different than an RBS detector. In fact, it is an RBS detector. We just place it behind the sample. So let's see what PIXI signal looks like. So we have an X-ray count on the Y scale, and then X-ray energy on the X scale. And then we have these X-ray peaks from the different elements that are present in your sample. And once we calibrate the spectrum, we can then identify which peaks on which elements are present in your sample. The RBS is similar. We have the intensity or counts on your Y scale, and then we have the channel number. So this channel number is the electronic channel coming from the data acquisition. But once calibrated, we can convert this channel number to an energy scale. So going from high energy to lower energy, we can have heavy elements coming out at higher energy and lighter elements coming out at lower energy. The energy scale also gives you an idea of the depth. So if you have a single sample, a single thick sample, the backscattered energy from the surface will be much higher than the backscattered energy from deeper inside. So the energy scale can also be converted to a depth scale if you have a thick sample. So the surface energy will be higher compared to the energy coming from the bulk of the sample. Okay, so that's what a typical RBS spectrum looks like. And then the stim spectrum is again, counts versus channel, or in this case, again, it's an energy scale. And in this case, it's the forward scattered ions coming out. So, and if it's a biological cell, your counts for carbon and hydrogen will be huge, because that's what hydrocarbons are mainly present in cellular structures. So you will have these two peaks, predominant peaks of carbon and hydrogen in a forward scattered off-axis stim spectrum. Carbon being heavier comes out at a higher energy compared to hydrogen. Okay, so these three spectra are typically always collected at the same time. Most of the times, what we do is we do Pixie and RBS together. These two are never done by themselves. We always collect Pixie and RBS signals together, and then depending on whether we need to do STEM, or whether we need to do gamma measurements, or whether we need to do some other techniques, we will have that respective detector inside and collect those signals. So in this case, it's a STEM signal. If we put a gamma detector, we can get a gamma output from the sample, along with the Pixie and the RBS outputs. So this is what a typical experimental day at SIBA would look like on at any given time. And moving on to then the imaging techniques and the resolutions. So kind of expanding a little bit further on the STIM part of the measurement. So like I said, STIM stands for Scanning Transmission Ion Microscopy, and this is also one of the commonly used techniques in SIBA. But STIM can be further identified into two kinds, depending on how and where you place the detector. Okay, so if you have a cell with an incoming beam of incident ions, if the cell is thin enough, these ions will be transmitted through the cell. Now, if you place the detector right along the axis of the incident beam behind the cell, what you're going to get is a signal of forward transmitted ions. If you place the detector off axis of the incident beam, what you're going to get now is a signal of the forward transmitted, but they are scattered, forward scattered ions. Okay, and then if you look at the two images, this is the image taken from an on-axis stem, that is from this detector, and you look at this image. This is the one taken from this detector. The resolution of the on-axis stem image is extremely good. Right, so we typically get about 40 nanometers of resolution for on-axis STIM images. But the downside to that is this detector faces the ion beam, or is right in the path of the ion beam. So by keeping this on-axis for a long time, you are reducing the life of the detector. So if you keep on taking on-axis STIM images, eventually your detector will get damaged. Right. So compared to that, if you look at the off-axis STIM image, now the off-axis STIM image, because it's an image taken from the forward scattered ions, the resolution is not as good as the on-axis STIM image. It's about 100 nanometers, sub 100 nanometers. But here we have a very distinct advantage that we don't get in an on-axis STIM, and that is we can get elemental contrast from an off-axis STIM image, because these are forward scattered ions. So now we can identify based on the energy, different elements that, based on the energy of these forward scattered ions, the different elements that that could be present in your sample. We cannot get this in an on-axis STIM image, right? So while an off-axis STIM image will preserve your detector and give you elemental contrast, you lose out on the resolution. But for an on-axis STIM image, you get good resolution, but then you have a higher chance of damaging your detector. So that doesn't mean that we don't do on-axis STIM. We do on-axis STIM imaging, but we keep it to a minimum, a bare minimum. So if you want a good high resolution image, you will just take one image of an on-axis STIM, one image of the sample using on-axis STIM, and then the same detector, we switch it to an off-axis mode, and then we start collecting forward scattered ions in the off-axis mode, where we then get this elemental contrast as well. And here what you see is this is just a fluorescence detector that we sometimes place in there in case you have fluorescent particles in your cell. We can use or detect these fluorescent particles using this fluorescence detector. But the idea being that the fluorescence compared to the on-axis and off-axis stem gives a very poor resolution. So we typically don't do this unless it's absolutely necessary. We kind of stick with on-axis and off-axis stem imaging, and that too within this we will mostly stick to off-axis stem imaging because we have this additional advantage of elemental contrast. And to expand a little bit further on that, I just want to show you what I mean by elemental contrast. Okay, so this was an elemental mapping of a rabbit artery tissue. This was an old project. This was done much before I joined in. This was a section of a rabbit artery that was on a high cholesterol diet, and it was taken after 8 weeks on a high cholesterol diet. And what they wanted to do was they wanted to basically image this section and find out the different elements that could be present in this section. So they gave us a stained optical image. So this is the stained optical image of the rabbit artery tissue. What we did was we went on and collected an off-axis stem image. Right. So this is what the off-axis stem image looks like of this section here. So obviously the resolution is not very good compared to an on-axis stem, but we do have some elemental contrast. Okay, so and just like I said to you before, when we do off-axis stem imaging, we also do we collect pixel signals as well. So we are collecting X-ray signals at the same time. So from the X-ray signals, we are now able to identify which elemental peaks are present in your sample. So if we select these elemental peaks from this off-axis stem image, what we can now get is these different elemental maps, right? So we have an iron map, we have a copper distribution map, we have a calcium distribution map, we have zinc, and we have phosphorus. So they're all from the same section, but now you have elemental distribution coming out from the sample, right? And if you compare iron and zinc, you can clearly see the complementary effect. Where you have less of iron, there you have more of zinc. Where you have less of zinc, there you have more of iron. Right. So this is what I meant when I said that off-axis stem imaging gives you elemental contrast. Right. So we are able off-axis gives you the advantage of preserving your detector for a longer time. It saves your increases your detector lifetime. At the same time, you also have this distinct advantage of getting elemental contrast. So that's one of the reasons why we try to stick to off-axis stem imaging as much as possible. So the first image that we collect will be an on-axis stem image. Once we have a very nice clear image, a good resolution image, we immediately switch to off-axis stem and we collect data in off-axis stem mode, right? Because of this specific advantage. So that was the off-axis stem. Then there is a question of whether we can use protons or helium alpha particles for STEM, and of course we can use protons or alpha particles for STEM imaging. But then again, there are pros and cons to it. Alpha particles being heavier, they give a better imaging contrast for helium STEM. As you can see here, the contrast is much better. For proton STEM, because protons are lighter, we lose out on the contrast or the resolution, right? But helium being heavier, what if we are doing helium STEM, we need to be careful as to how thick a sample we are putting in. If the sample is fairly thick, you're not going to get any transmission of helium through your sample because it's quite heavy. It's going to get stuck into the sample itself, and then you won't have any imaging at all, right? Whereas protons being lighter, they have a much better depth into your sample, and we have the flexibility to use slightly thicker samples as well, right? So if you're willing to lose out on the imaging contrast to a certain extent, we are better off using protons because we know that for certain certain sample thickness ranges, we will definitely have a transmitted signal coming out. So there are pros and cons to both, and most of the times we use protons for STEM imaging. We don't try to use helium because for our purposes, proton STEM imaging is quite okay. We have been quite happy with what we have got so far. But we can, I mean, you can use helium alpha particles for STEM imaging as well. So when you talk of helium being used um, uh, as a particle for for imaging, the question then also comes as to what about helium ion microscopy? What's the difference between helium ion microscopy and helium STEM imaging? So, of course, helium ion microscope, has its own very distinct advantages. So, this is an image taken by a helium ion microscope of a human liver cell. It has a very good spatial resolution, about 3 nanometers, right? So, we took the same image in a helium STEM setup, and this is what we got, right? So, what we now see in a helium STEM image is that the spatial resolution has slightly dropped. So now it's about 40 nanometers. But what we are able to get from a helium STEM image is the internal structure of the cell, right? We are able to see the cell nucleus. We are able to see what's inside the cell nucleus, right? So we do not get this from a helium ion microscopic image. Now, that doesn't mean that the helium ion microscope is a bad tool or a bad technique, or helium STEM is a bad tool or a bad technique. The point being that both these techniques should be used complementary to each other. And if we are able to do that, what it gives us is a lot more data, a lot more material to work with, to analyze for, right? So if we just stick to one technique, we are restricting ourselves in terms of the amount of data that we can get, for analysis. So having said that, both the techniques also have their pros and cons. So helium ion microscope, as most of you all know, it's kind of a tabletop, not exactly a tabletop, but it's a setup that can be put in a small room, and we can work with it. Whereas a helium STEM setup is not exactly a small room setup. We need a whole array of beam lines. We need an analyzing magnet. We need a huge accelerator to work with it. So it's a fairly large setup compared to a helium ion microscope. Right? But you have this additional information that you can get when you do helium STEM compared to a helium ion microscope. Right? So pros and cons are there, but as long as you use both the techniques complementarily to each other, there is a good scope for collecting a lot more information, and being able to analyze your data in a much better way. Right? So usually we get this question as to when we show people helium ion STEM, they always compare it to helium ion microscope, and then we always show them this image that these are the two techniques, and they are complementary to each other. So they not one is good or the other is bad. It's that they are complementary to each other. So coming to proton beam writing. So like I said, this is materials modification technique, which was kind of started and developed by one of the senior professors in SIBA back in the early 1990s, I believe. And so this technique is not any different than e-beam lithography, or for that matter, any lithographic technique. So what we do here is we start with a substrate. We spin coat either a positive, or either a negative or a positive resist, expose the resist to proton beams. So if it's a negative resist, wherever it is exposed, it will solidify. If it's a positive resist, wherever it is exposed, that part will get dissolved. Then we have the chemical development stage. Then this then becomes like the master mold at this point. We then electroplate this with nickel, and we take away the mold. So what is left behind is a nickel template, which we can then use to replicate the structures by a process called hot embossing. Okay, so the process flow goes like this. It's proton beam exposure to your surface, chemical development, electroplating, and then hot embossing. So when they first tried this technique, they wanted to show the applicability of this technique. They wanted to see how good this technique works. So they went on and they created these structures. So they went on to create the miniature of the Parthenon in Greece. So this is on the micron scale. So this was done using proton beam writing. They also went on to create a miniature of the Stonehenge that is there in the United Kingdom. Again, this is on the micron scale, right? So this, they just wanted to show how good proton beam writing can be and what is its functionality, what are its limits. So this is what they did back in the 1990s. But today, what we actually use proton beam writing for is to create these kind of high aspect ratio structures. Okay, so this was done in a 10 micron thick SU8. So you can see how high the aspect ratio is. So this is 60 nanometers and this 10 microns deep. So if this is 60 nanometers, that means the beam spot that they focused in, the focused beam spot that they got has to be much lesser than 60 nanometers, right? So they were literally pushing the beam line to its limit to get these structures. Here it's a 120 nanometer, slightly bigger, double this with the same SU8 thickness. Right. So we now use proton beam writing to kind of create these high aspect ratio structures. So here, we have made these waveguides. So that's the advantage of using high energy protons, for proton beam writing, because protons, depending on the material, have the ability to go fairly deep inside the material with minimum or negligible scattering. So we can have these high aspect ratio structures if we are able to focus the beam spot down to sub 50 nanometers, right? So this is one of the distinct advantages of proton beam writing. We in fact even have created micro and nano channels now to for microfluidics and nanofluidic research projects. But again, the downside to proton beam writing is that it's not something that can be set up in a small room. We need an accelerator to run the beam through the beam lines and into the chamber. So that's proton beam writing. And finally, coming to the materials analysis part of it again. Rutherford backscattering, like I said, is something that I mainly work with. And so I just wanted to share with you some aspects of Rutherford backscattering. And more specifically, RBS is kind of a broad area, and I cannot cover all of RBS in this, but I did want to kind of focus on one aspect of RBS, and that is ion channeling. Ion channeling also is kind of a broad area, but I just want to give you a brief idea of what ion channeling means, from a materials analysis point of view. So RBS, or rather ion channeling in layman's terms, right? So when you have an RBS setup, what happens? You have an incident alpha particle coming in towards your sample at a very high energy. When it collides with the sample, some of those particles will backscatter, and depending on what element you have in your sample, there will be a specific backscattered energy that will be there for the backscattered particle, for the backscattered helium particle. If you're able to detect that energy, that will tell us what element we have in your sample. So if you have gold, your backscattered energy will be very high. If you have silicon, your backscattered energy will be lower. So we can calibrate this and identify which element we have in your sample. That is, in layman's terms, what RBS means. But if, let's say, if we have a single crystal sample, not gold, let's say we have silicon, which is a single crystal. So when I say single crystal, that means it has a crystalline structure to it. So let's say if I'm now able to align the atomic rows of these of this single crystal to the incident ion, what's going to happen to the incident ion? The incident ion is basically going to go straight into these atomic rows or these channels, right? So what that means is that ion channeling, so that in effect, or rather that in layman's terms, is basically ion channeling. You are taking the incident ion and you're aligning the substrate, the single crystal substrate, in such a way that the incident ion channels through the atomic rows of your single crystal substrate. So it's basically a gentle steering effect. I mean, in scientific terms, if you want to define ion channeling, it's a gentle steering effect by small angle scattering events with atoms that line the walls of the channel. Okay. So by this, what is one of the primary conditions you need to have if you want to have ion channeling? The first condition is that your substrate has to be crystalline. If you have an amorphous substrate, this doesn't work. So if you have an amorphous substrate, this particle will not go into your atomic rows. It'll just backscatter and give you a huge backscattered signal. So the first condition is that you need to have a crystalline substrate. Second condition being that you need to align this channel to your incident ions. If you don't align the channel, you're not going to be able to have this channeling effect, this incident ion going into these atomic rows, right? And what channeling does, so when you have an amorphous substrate, you have an incident ion, it backscatters, it gives you a huge backscattered signal. When you have channeling, what's happening to the incident ion? It basically channels into your atomic rows. So what's going to happen to the backscattered signal? You're going to have a reduced backscattered signal. So under perfect or optimum channeling conditions, your backscattering yield drops by up to 95%. Okay, and I will show you how the spectrum looks, compared to an amorphous substrate as against a channeled spectrum, or a random spectrum as against a channeled spectrum. There are distinct differences. So I will show you that in the following slides. But ion channeling technique typically is used. It has three specific applications. The first one being to detect lattice defects or strain or mismatch in your single crystal substrates. Okay, and I will explain this a little bit in detail as to what I mean by lattice strain and how we can measure lattice strain or a single crystal substrate strain by ion channeling. And the second and the third applications of ion channeling is to reveal small impurity peaks that could be buried in your single crystal, or also to measure the location impurities, to measure the quality of your crystal, whether your impurities are substitutional or interstitial. And these two I will kind of touch upon when I talk about the project that I worked on at SIBA, the germanium-based project. So I will kind of touch upon these two applications when I talk about that project. But first, I will just give a brief introduction of what I mean when I say that ion channeling can be used to measure this strain. Okay, so if you look at ion channeling, right, this is what a typical RBS spectra looks like. This is a typical random RBS spectrum. Okay, so when I say random, I mean that your substrate is either not crystalline, that is, it's amorphous, or it's a crystalline substrate, but you have not aligned the atomic rows to the incident ions, and which is why you get a huge backscattered signal. Now, when you have channeling, what's going to happen? Most of the ions, incident ions, are going to go into the channel, and what that is going to do is you're going to have a significant drop in your backscattered yield. Right. So now this was a backscattered yield in random mode. But once you have aligned your channel to the incident ion, this is what your backscattered yield looks like. So there is a significant drop, right? And then you have this characteristic feature that you will always see for a channel spectrum. Okay, it's called as a surface peak. What that means is, if we are able to visualize the atomic rows of a single crystal silicon from a horizontal perspective, okay, from the side. So we have these top row of atoms and the bottom row of atoms. And let's say we have aligned this atomic row to the incident ion beam. So we have these alpha particles coming in here. What's going to happen, because the channel is aligned to the incident beam, most of these ions are going to go straight in, and they're going to have this spiral path as they enter the channel, right? And that's what is going to give you a drop in the backscattered yield, because all of them are going in now, nothing is backscattering, right? But what happens here at the edge? You have these two atoms at the surface, right? So these two atoms at the surface, they will deflect the incident ions that hit them, right? So these incident ions, some of them, the ones that are here and the ones that are here, they will collide and deflect from these surface atoms, and that gives rise to what we call as a shadow cone effect. Okay, so what that means is that these surface atoms are essentially shadowing all of these atoms that lie below them. right? So when you have these incident ions come and collide with these surface atoms, you get a shadow cone effect, and the ones that collide from here will backscatter. So these are the only two backscattering events that will occur when you have channeling. Most of these incident ions will enter the channel, except for the ones that collide here and here, they will backscatter from the surface atoms, which is why you will, in a channeling spectrum, you will have a surface peak. That is why we call this as a surface peak. So this is a very characteristic feature of a channel spectrum. Okay, if you don't get this peak right, then that means your channeling is not good. You're having some problem with channeling, or or it's not a single crystal anymore. Excuse me. Okay, so the moment you see this peak, that tells you that you are definitely getting into the channel to some extent, or you are channeling to some extent. Okay, so this is what a typical random and a aligned or a channel spectra looks like. And if we are, and of course, as these particles go in, right, eventually they will start, once as they enter the channel, eventually they'll start to dechannel, and then slowly your yield will start to go up. But then we are not concerned much about this part of the spectrum. What we are concerned about is mainly this part of the spectrum. And if we compare the random counts to the channel counts, this drop in the counts will give you an idea or an estimate of how good your crystalline structure is for your sample, for your silicon. Okay, if your silicon is perfectly crystalline, you will have a very good channeling effect. This difference will be large. That tells you that your crystal is of good quality. If your single crystal is not of good quality, your channeling will not be as good as this. So you will have your channel spectrum coming out from a here, and then this difference will be smaller, which means your crystal quality is not good. Okay, so this kind of gives you an idea as to how good a crystal you are working with. If you're able to get a very good channel spectrum, that tells you that your single crystal is of very high quality. And then when we talk of channeling, again, there are two kinds of channel spectra. Okay, depending on where you are in your atomic on your atomic lattice. So let's imagine these to be the channeling planes. Okay, if these are the channeling planes, at the intersection of these planes, you have this axis of your channel. If you are able to align your incident ions exactly to this axis, what you're going to get is what we call as an axial channel spectrum. Okay, so this is an axial channel spectrum where you will have a minimum yield, minimum backscattered yield, if you are right on the axis. Uh, if you're on the plane somewhere here, what you're going to get is a planar channel spectrum, and in this case, your backscattered yield will be slightly higher, not as good as the actual channel spectrum. You will still have a surface peak, but your backscattered yield will be slightly higher. And of course, if you go off these 2 points somewhere here, which is the random direction, your backscattered yield is going to be fairly huge. Okay, so for the sake of materials analysis, right, what we are usually concerned with is the random direction and the actual direction, actual channel spectrum. We want to find out the difference between this and this. We are not really concerned about planar channeling. But that doesn't mean that planar channeling is not useful. Actually, it is useful in a way that if we want to find the axis, what we typically do is from the random direction, we will try to first find the planar channel of the planar direction. Once we are there, then we just go along the plane until we come right at the axis. Right. So although this is not used in the data that we collect, it is useful for us to, it helps us to find where the axis is located. For single crystal silicon, it's not that big a problem because 100 axis or 111 axis is pretty easy to find. But in some cases, some of the complex crystal structures, it's not easy to find the actual channel. So then what we do is from random orientation, we will try to find one of the planes, and then we just travel along that plane until we have a drop in your backscattered yield that tells us that now we are now in the axis or along the axis. Okay, so we have planar and axial channel spectra that kind of form part of ion channeling. Um, Moving on to lattice strain measurement. Okay, this is one of the applications, like I said, for the ion channeling technique. Now, why is this important? Why is lattice strain so important? So, if you're familiar with semiconductors, or if you're familiar with electronic materials, right? A lot of these electronic devices, they use some sort of an amorphous film, an oxide film, on a single crystal substrate. So we have silicon oxide on silicon, then we have hafnium oxide on silicon, and nowadays they are using hafnium oxide on germanium. So what happens is, when you have this amorphous film on a single crystal lattice, right at the interface, right, and there will be some amount of strain in the crystalline lattice. Why this strain comes is because you're going to have a lattice mismatch, right? Hafnium and oxygen have different atomic sizes compared to germanium. So that lattice mismatch is going to give you some amount of strain in your single crystal lattice. So as you can see here, this lattice here close to the interface is strained, whereas in the bulk, it is a perfectly single crystal, right? And then this strain can be either tensile or compressive, depending on what kind of a mismatch you have. So from an electronic point of view, or rather from an electronic property point of view, this strain actually can be useful. Now, of course, if you have too much of strain, that is not good. But some amount of strain actually is useful in enhancing the electronic properties. So that means that we want to know, when we deposit these kind of thin films on these single crystal lattices, we want to know what is the amount of strain you have in this lattice. And also, we want to know whether that strain is compressive or tensile, right? So there is a need to find out what kind of a strain there is and the amount of strain. And that is where ion channeling and RBS becomes very useful, because ion channeling and RBS are one of the I believe they are one of the only techniques where this kind of lattice strain measurement can be quantified, or one of the most used techniques, for quantifying lattice strain. So let's see how this works. So let's say we have this hafnium oxide film on germanium lattice. The first thing we do is we have an incident beam. We align it to a channel. In this case, it's a 111 channel. So this is a perfectly channeled beam that goes along the 111 direction. We measure the spectrum. So that's our first spectrum that we measure. This is the channeled spectrum. Then we start tilting the crystal, tilting your substrate in the positive theta direction and the negative theta direction. So we will go plus 0.2, plus 0.4, like two thetas in the plus direction, and then we go minus 0.2 and minus 0.4. So we have a total of 5 spectra that we collect. First one is the channel spectrum. Then second one is the plus 0.2. Third one is the plus 0.4. The fourth one is the minus 0.2. Fifth one is the minus 0.4. Okay, so we have 5 spectra that we collect from the first measurement. And one second. Yes. So once we have these 5 spectra, then we put these 5 spectra together on one plot or one graph, and so kind of a superimpose these 5 spectra together, and we split the x-axis along the x-axis. We split it into different regions. Philip, are you trying to say something? Okay. So once we collect the 5 spectra, we put all of them together on one plot, and we divide the x-axis along these. Divide the x-axis with in these. Hello. Yeah. So we then. Hello.
Yes, sir. There is nothing wrong, sir. You can just continue.
Oh, okay. There's a lot of background noise. I thought, okay. All right. So once we have these five spectra, right? So we then put these five spectra together on one graph, kind of superimpose them, and we split the x-axis or the energy scale into these different regions. Okay, um, and so what these regions mean? Okay, so this is the high energy region, which means that it is corresponding to an area that is closer to the interface. This region here is somewhere slightly comes at a lower energy, which means this is coming from somewhere below the interface, somewhere much below the interface. And then this region comes at an even lower energy, which means this is coming almost from the bulk, where the strain is not affecting the crystal structure. It is the crystal structure is quite good, right? Then what we then do is we collect these counts from each of these regions and we plot them on the tilt axis, right? So we have the counts and then we have the tilt axis. So this is the tilt we gave to the crystal, right? Once we do that, what we get is these set of curves, which are called as angular scan curves or rocking curves. Okay, so what do these curves mean? Okay, so if you look at this bottommost curve, curve G, right, at the lowest point here, this lowest point has the lowest counts, lowest backscattered counts compared to all the curves, which means that the channeling at this point is really good. That means this curve corresponds to this region here, which corresponds to this part of your sample where the crystalline structure is good and the channeling is good. Therefore, your counts are the lowest. You go up in counts, come to curve D. Now your counts are higher, which means the channeling is not very good. That means it is coming from somewhere this part of your spectrum. This part corresponds to somewhere this part of your sample, where now it is closer to the interface. It is slightly strained, and therefore you have your channeling is not good, and therefore your counts are also slightly higher. And if you come all the way up, all the way to A, this is even worse, right? So this has the highest counts, which means you are somewhere coming from this part of your spectrum. This part corresponds to an area which is closest to the interface, which is extremely strained, and therefore your channeling is going to be even worse, and therefore your counts are going to be even higher, right? And then each of the points on these curves correspond to the tilt degrees that we gave, right? So we started from the channeled orientation, which was the 0 degrees. Then we went plus zero point 0.2, we collect a spectrum. We went plus zero point 0.4, we collect a spectrum. Then we come back to minus zero point 0.2, we collect a spectrum. Minus zero point 0.4, we collect a spectrum, right? So there are 5 of these spectra that were collected. And when we put all of this together, this is, these are the set of curves that we get. Once we have these set of curves, then we look at the lowest, the first curve here, the G, and the local minima of G, and compare that to the local minima of the of curve A, right? So curve A corresponds to this region here near the interface. Curve G corresponds to this region here in the bulk. So we are essentially comparing the channeling from the bulk towards comparing channeling from the bulk to the channeling near the interface. So we're comparing the local minima of G to the local minima of A. And by looking at the local minima, the shift in the local minima of A from G, we can then get an estimate of how much strain we have in the sample. And the direction of the shift will also tell us whether it is compressive or tensile. So in fact, there is even a formula for that. So this is the same set of curves I showed you before. And the angular shift in the channeling dip. So this is the channeling dip, right? So angular shift that goes from here all the way to here is what will give us an estimate of the lattice strain. Okay, and then of course, if the dip shifts towards a larger tilt angle, with decreasing depth, that gives us compressive strain. And if it shifts towards smaller tilt angles with decreasing depth, that gives us a tensile strain. So by looking at which direction the dip shifts, that tells us whether it's compressive or tensile. Right. So this is one of the quite unique features of RBS and ion channeling. In that it gives us the ability to measure, not only quantify, but also tell us now whether it's compressive or the kind of strain that we have in the single crystal lattice, right? So that was the strain part of RBS and ion channeling. I now want to move on to the the first project that I did in SIBA on germanium lead thin films. And so the objective of this project was, so we know that silicon technology is kind of getting saturated now, and people are looking at other alternative materials for silicon. Germanium being actually one of the potential candidates to replace silicon in the near future. Why germanium? Because germanium has a higher carrier mobility compared to silicon. But germanium, just like silicon, is also an indirect bandgap semiconductor. So if you want to make it into a direct bandgap semiconductor, we need to dope it with impurities like lead and tin. And so what we were trying to do here was we wanted to see the how lead as an impurity dopant behaves in a germanium lattice. So we had these germanium lead thin films that was sputter deposited, and we wanted to see whether a pulsed laser annealing process works as a dopant activation for lead in germanium. And what we also wanted to see was to see whether lead stays in the germanium lattice, or whether lead moves in the germanium lattice, whether it moves towards the substrate, or whether it moves away from the substrate. So what we did was we put in some capping layers on top of these films, and then we wanted to see we wanted to monitor the motion of the movement of lead within this germanium lattice. Okay, so that was the objective of this project. And this was the thin film process flow that was followed in making these samples. So starting from a germanium substrate, so these were sputter deposited germanium lead films. As deposited, they came as alpha germanium lead, and then after the pulsed laser annealing step, there was a phase change to C germanium lead. The capping layers that we used were silicon oxide, silicon nitride, and aluminum oxide. And then these are the pulse laser parameters that were used to activate the lead within the germanium. So to start with, we when we first got the samples, we just did a conventional RBS on these samples. So we had 4 samples. We started with the bare germanium lead. This was the reference sample, and then we had these 3 capped samples: silicon oxide, silicon nitride, and aluminum oxide. We did a conventional RBS. So this is a typical RBS spectrum. So typical dopant levels for converting semiconductor to a direct bandgap semiconductor, the dopant levels are fairly low. They are on the order of 3% or even lower. So the lead is not going to be very significant when you see it in RBS. So we had to zoom in, but once we zoom in, this is what we see. We have the lead from the reference sample coming out at a higher energy. Why? Because it's on the surface. And then we have the lead from the cap samples, which come out at lower energies because of the capping layers on the top. Right. So this was our starting point. We then went ahead and did the pulsed laser annealing step on these samples and took out the capping layers and did the RBS measurements again. Right. So this was after the pulsed laser anneal without the capping layers. So now all of these capping layers have been taken off. Now we still have the reference sample, and we still have the lead from the reference sample. Also, all of the lead peaks are now aligned. Why? Because the capping layers have been taken off. So all of the lead is now on the surface. Right. So all of them come at the same energy, but there is a distinct difference. The reference sample lead is still there, but the lead from the cap samples has significantly dropped. Right. So what does this tell us? This tells us that after the pulsed laser annealing step, after the dopant was activated, there is a movement of lead, and that movement of lead is not basically towards the germanium lattice, but it's rather away from the germanium lattice. What happens is lead gets activated, and due to some kind of an internal process, which we don't know yet as to what exactly it is, that lead gets into the capping layers, and when we etch the capping layers away, we have lost pretty much most of the lead. Right. So we have some lead left behind, but that is not something that we wanted. We wanted to have more lead in the sample, but we lose most of the lead into the capping layers once we have the pulse laser annealing step done. And then with whatever lead we have left, we wanted to now see whether this lead is in the substitutional site or the interstitial site, right? So we wanted to see whether the quality of that film with the lead being in there is good or not. So for this, then we went on to do high resolution RBS measurements in channeled and random mode. This cannot be done in conventional RBS, so we have to go down to no, we have to use a high resolution RBS system to be able to resolve these lead signals. So this is a random signal from germanium. This is a channel signal. Then just like I told you told you previously, we have this surface peak that comes from a channel spectrum. The same thing applies for lead. So if you zoom into the lead, we can have, you see that the channels spectrum from lead also has a surface peak, and then this is a random signal. And then if you compare the random to the surface to the channel spectrum, we have about 70% of drop, right? So that tells us that the lead substitution behavior is on the order of 70%. We were hoping for more, but 70% was still quite good enough for us. We didn't expect it would be this good. We compared this to silicon nitride. We did the same thing with silicon nitride. So there also we got about 71%, and then this one was the worst of the lot. So aluminum oxide, the substitution behavior was only about 63%. So this is again with whatever lead is left behind. Now, most of the lead has been lost in the capping layers. This is only with the lead that is left behind. And then, just like I told you before, we corroborated this data, with the complementary technique. We did a cross-sectional TEM imaging on all of these samples, and this kind of corroborated our analysis from RBS. The silicon oxide and silicon nitride, the lead substitutional behavior was much better. So you can see from the lattice, from the TEM image here. Compare that to the aluminum oxide. We had all these development of cavities in the germanium lead layer after the pulse laser annealing step, right? So that's kind of matches with what we got from the high resolution RBS measurements as well, right? So this was our kind of a conclusion for this project, that pulse laser annealing doesn't really works to some extent, but not to the extent that we were hoping it would, to in keeping lead inside the germanium, so that we can convert the germanium lead to a direct band gap semiconductor, right? So this kind of brings me to my last slide, which is proton beam therapy. As I said, I just wanted to touch upon this one aspect of SIBA that we are working on. And so here again, I bring up this figure here of the protons entering into a material, and the minimum scatter you see as they enter, and at the very end they have this huge peak called as a Bragg peak, which comes up because of the loss. They lose all of the energy at this Bragg peak. So they come in with minimum loss in energy, and they lose all of their energy at this Bragg peak. And I told you before that these two features are extremely useful in making proton beam therapy work. So if you compare this, to an X-ray treatment, okay. So let's say, so I'm just superimposing this on an X-ray treatment curve. So let's say you have a tumor in a human body. Okay, you expose that tumor to an X-ray dose. What's going to happen? You're going to have an entrance dose. So as the X-rays enter, the moment the X-rays enter, your body is going to experience the dose. The tumor is then going to experience the dose, and then you're also going to have an exit dose. So as the X-rays exit the body, your body will still experience a dose, right? So from the time the X-rays enter the body, your body is experiencing an X-ray dose. So it's not only the tumor, but the other parts of the body also get affected, right? Now you come to this aspect and use this and combine this with the fact that you have a tumor at a certain point in your body. So let's say if you have a tumor at a certain point in your body, you're able to tune the proton energy to such an extent that all of this energy loss, the black peak energy loss, happens exactly at the tumor here, right? So what happens as the protons enter, they have minimum scattering. So you have some amount of entrance dose, but it's negligible. So your body doesn't get that badly affected. At the tumor part, it deposits all of its energy, so the tumor gets burnt out. And beyond that, that's it. There is no more. The protons don't go beyond that. So there is no exit dose when it comes to proton beam therapy, right? So what I'm trying to say here is that proton beam therapy offers a more targeted approach to tumor treatment, cancer treatment, right? That is why this is one of the hottest research topics, medical research topics as of now. And a lot of medical centers and institutes across the world, including US, Europe, Japan, they have set up these facilities, in their countries. Singapore is trying to set up a similar facility in Singapore, and that's the reason why we are working with the National Cancer Center of Singapore. They want us to kind of build a prototype and get the initial data so that they can then use that data to build an entire system. So that's where that's why I wanted to touch upon proton beam therapy, because it's a very active part of active research part of SIBA as of now. Okay, and that kind of brings me to the end of my talk. It's almost time as well. So just to summarize, on ion beams, the positives that come out from ion beams is that there are a lot of opportunities in material science for ion beams. In terms of what kind of research you can do, and it's not only material science. You can even branch out to other areas of material science where you can use ion beams. Like for example, proton beam therapy in medical science. Right, people are using protons now in medicine to treat cancers. Right, so there are a lot of opportunities still available in research areas for ion beams. The negative part comes in the thing that these kind of labs are not cheap. They are very expensive to set up and maintain. And then there are obviously safety concerns. No institute or university want to have a lab that could be a radiation hazard. So there are always safety concerns when you talk of ion beams and when you talk of accelerator labs. So with that, no, I think I will kind of wrap up my talk. Thank you for your attention, and if you have any questions, I'll be happy to take them now. I kind of shot over the time, but sorry about that. But thank you.
Thank you, sir. Thanks a lot. Techniques are the gods of science, and that's true. Your pure knowledge on optical technology has widened your perspective of science. There are a few questions that the participants have loaded. I'll just tell you. The first question is from Kishore. Can we take in situ images for human body by STIM?
In situ for human body. You mean what? That then the question is, you're talking about live cells or dead cells?
Sorry, that was not given. The plain question is
Okay,
that can we
so
take in situ images? I
yeah, we
think it's
can.
about life cells.
Yeah, that is why that is something that we are working on right now. We are working on imaging live cells. So there is a bit of a challenge there. When you talk of live cells, you are putting them in open air. And you want to get ion beams out into open air and interact with a human body. So the moment they come out in open air, you're going to have a lot of scattering of these particles, right? So right now, what we are working on is to just image cells. Human body will be the next step, possibly, but right now we're just imaging cells, uh, putting them in open air, and getting these ion beams out into open air with a minimum scattering effect, and seeing how these cells get affected, live living cells, how these living cells get affected with these proton beams or alpha particle beams. Right? The human body will possibly be the next step.
Next question is, which software is used to calculate molecular docking?
Molecular
Docking.
molecular talking.
GO. Yeah, molecular docking.
I'm not aware of. Molecular talking is. Could you spell that again?
DOCKING, docking.
GOCKING.
D, D, DOCKING, docking.
Docking, I mean.
Yeah,
Molecular docking.
yeah.
I'm not really aware of that.
Okay.
Uh, yeah,
Okay, we'll just
yeah.
ignore this question. Next question is from Shantini Grace. Can you please explain about the side effects when a body is exposed to STIM?
Scanning transmission. Uh, I mean, I would estimate. I would say it would be depending on if you're using alpha particles or protons. Um, the side effects would not be as much, depending on what energy you're using. You would have transmission of these protons through your sample, but then so I'm kind of not understanding. So when you talk of human body, you are not going to have a stim effect because stim is scanning transmission ion microscopy. So you need the particles to transmit through your body, right? So if you're looking at a 2 MeV particle beam, it's not going to transmit to your human body. A human body is very thick. You have to thin it down to micron level or submicron level cellular structures. So the question is a little. I'm not able to understand the question.
Yeah, but that was the
Yeah.
question.
Okay.
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 The next question is from
Yeah. Yeah.
Uma Baradan.
Okay.
What is scattering yield? Is it the yield strength? She wants you to define what is scattering yield.
Scattering yield is the so when you have an incident ion particle coming and colliding with your sample. Let's say you have 1,000 particles coming in and colliding with your sample. Out of the 1,000 particles, there will be like few of them, very few, like 1% of them that would backscatter. So they will collide and they will backscatter. So that backscatter is what the scattering yield is that I was referring to,
Okay.
right? So
The
if you
next
have
question is from J. Tirupati.
yes,
You want to answer still?
no, you can
If
go
you
ahead.
want, you can proceed on, sir.
No, I was saying that if you have instead of 1,000 incident ions, if you have 1 million incident ions, then a backscattering yield will be higher. At the same time, for the 1,000 incident ions, if you have instead of silicon, if you have gold, gold is being a heavier particle, gold will backscatter more. So your backscattering yield from gold will be higher than silicon. That's what.
Next question is from J. Tirupati. He wants to know whether MATLAB can be used to detect lattice defects.
Can be if you can write a code in MATLAB, definitely yes. But we don't use MATLAB. 'Cause it becomes too cumbersome to write a code, and we have pre-programmed softwares to do these kind of calculations and to do these data fittings. They are very commonly used in ion beam analysis areas. But of course, MATLAB can be used if somebody can write a code. That would be very nice. We can also use it then.
Okay. The next question is from Julie Charles. What is the exposure limit of human body to these kind of radiations?
Exposure limits. I mean, we work with from my lab experience. I can say that the kind of exposure limits we have are way below the limits that any human body can handle. I don't know the exact number if you're looking for that, but we work in our lab without any radiation badges because the kind of radiation that comes out of our accelerators are extremely low. Unless we run certain specific experiments, then we have certain radiation issues. But just with protons and alpha particles on standard materials, exposure limits are very low. I mean, the radiation is very low. So
The next question from Eunice. Do we get images as like SEM or TEM, or can it be used for any morphological study?
uh, Not really. So when you talk of STEAM imaging, right, that's why I mentioned specifically the fact that two techniques have to be used complementary to each other. So when I showed that helium ion microscopy image, that gives you a very nice surface topography, surface resolution, right? But a STEAM image will give you something that is inside your sample, inside your cell, and that's what it does because it's a transmission ion microscopy. So it goes through the sample, it images what is inside the sample. So you will lose out on surface topography or surface resolution, but you have certain information that a helium ion microscope will not, or a standard SEM will not give you, right? So you have to use both these techniques together complementarily.
Okay, the next question is from Dr. Rekha Pachayapan. What is the allowed number of STIM in the treatment of cancer?
What is there? What is the what level?
She's asking for some allowed number. Which number is allowed? How many? What are the numbers of allowed that is in STIM in the treatment of cancer? But I think the question is incomplete.
Okay, because so no, I actually don't understand the question. Alone, I have not heard of this.
Even I don't.
Yeah,
Even I don't. Okay. Okay,
sorry.
sir. I think it's okay. No problem, sir. Okay, I think that's the questions for this session. Thank you so much for your
Yeah, no
valuable
problem.
ideas about technologies and techniques.
Yeah,
Have a great day ahead. Thank you so much.
yeah.
On
Thank
behalf
you,
of St.
Professor
Joseph
Ramya.
Institute of Technology, we thank you, sir. We thank you a lot. Thank you.
Thank you. No problem. My pleasure. Yeah.
Yes, sir. Thank you. Thank you, participants. I hope the session should be so informative for you. And tomorrow from 12 o'clock to 1:30, we have another session by Dr. Paul Joseph, Assistant Professor in NIT Warangal from Physics Department. His talk is about ultra-thin, transparent, conducting metallic multi-layers. Okay? They would like to join you in that. Okay, thank you. Thank you, sir.
Thank you.